this module, you will learn about the arrangement of elements in the modern periodic table based on electronic configurations. The long form of periodic table is the most widely used modern periodic table. It arranges all the known elements into 7 periods and 18 groups based on their electronic configuration. Why use electronic configuration to decide arrangement of the elements? To find the answer to this question, let's first review what electronic configuration means. The term electronic configuration refers to the distribution of electrons in the shells and orbitals of an atom. The principal quantum number of a shell, n, defines the energy level of an electron and gives its distance from the nucleus. Shell is further divided into subshells. These are S, P, D and F. The electronic configuration of an atom defines its physical and chemical properties. For example, as we go from left to right in a period, the atomic size keeps on decreasing. This happens because as the atomic number increases, more electrons get added to the same principal energy level. Due to the same effective distance of electrons from a more positive nucleus due to additional protons, electrons get more strongly attracted to the nucleus, thereby decreasing the atomic size. However, the principal quantum number increases as we go down a group, as the outer shells are more shielded from the nuclear attraction due to additional layer of electrons, and distance from the nucleus as compared to the previous level. This results in increasing atomic size with increase in atomic number. The chemical properties of elements depend on their electronic configuration for the same reason. The elements with higher principal quantum number more readily take part in chemical reactions due to weakly bound outer electrons. The chemical reactivity, however, decreases with increase in atomic number for the set of elements having the same principal quantum number. Likewise, the other physical and chemical properties of elements, such as density, boiling and melting points, ionization energy, electron gain enthalpy, and electronegativity, also depend on their electronic configuration. These physical and chemical properties repeat periodically for elements having the same electronic configuration in their outermost shell, a trend that can be seen across the elements belonging to the same group in the long form of periodic table. The long form of periodic table arranges elements with the same principal quantum number n across a period, such that their electronic configuration changes only at the outermost shell. The number of elements in the period, therefore, depends on the maximum number of electrons that principal energy level or shell can accommodate. For example, the first period corresponds to the filling of electrons in the first energy shell or K shell, where n equals 1. Since this energy shell has only one orbital, 1s, it can accept a maximum of 2 electrons. Therefore, the first period has only 2 elements, hydrogen 1s1 and helium-1s2. The second period corresponds to the filling of electrons in the second energy or L shell, where n equals 2. It has a total of 4 orbitals, 1 2s and 3 2p, that can collectively accommodate 8 electrons. The second period starts with lithium with atomic number 3 and electronic configuration 1s2 2s1, ends with neon with atomic number 10. Neon has completely filled p shell and electronic configuration of 1s2 2s2 2p6. The third period corresponds to the filling of electrons in the third energy shell or M shell, where n equals 3. Although this shell has 9 orbitals, 1 3s, 3 3p and 5 3d orbitals, filling electrons in 3d orbitals is not energetically favorable as per Aufbau principle. You will learn more about this principle in the next module. Therefore, only 4 orbitals are available for filling electrons, which allow a maximum of 8 electrons in the outermost shell. As a result, there are 8 elements in the third period, starting from sodium, whose electronic configuration is 3s1, and ending with argon, whose electronic configuration is 3s2 3p6. The fourth period corresponds to the partial filling of electrons in the fourth energy level, where n equals 4. This is because, for this period, filling the 3d orbitals after the 4s orbitals and before the 4p orbitals becomes energetically favorable in accordance with the Aufbau principle. Therefore, this period contains 3d transition series of elements placed after potassium and calcium in the fourth period. The first element in the 3d series, scandium, has an electronic configuration 3d1 4s2. The last element in this series is zinc, having an electronic configuration 3d10 4s2, wherein the 3d orbital is completely filled. The fourth period ends with the element krypton with atomic number 36 and completely filled 4p orbitals. The fifth period corresponds to the filling of electrons in the fifth energy shell, where n equals 5. This period contains 4d transition element series, which starts with yttrium, that has an atomic number 39, and ends with cadmium with atomic number 48. The first element in the 4d series, yttrium, has an electronic configuration 4d1 5s2. The last element in this series is cadmium, having an electronic configuration 4d10 5s2, wherein the 4d orbital is completely filled. In the fifth period, electrons enter into the 5s, 4d and 5p orbitals successively. The fifth period ends with xenon with atomic number 54 and completely filled 5p orbitals. The sixth period corresponds to the filling of electrons in the sixth energy shell, where n equals 6. It contains a total of 32 elements and follows the orbital sequence of 6s, 4f, 5d and 6p. This period contains the 4f inner transition series of elements after cesium and barium, also called the lanthanoid series. The lanthanoid series starts at cerium and ends at lutetium. The seventh period consists of most of the man-made radioactive elements that have 7s, 5f, 6d and 7p orbitals filled. This period also contains 32 elements, including the 5f inner transition series called the actinoid series. The actinoid series starts at thorium and ends at lawrencium. It may be interesting to note that the number of elements in each period is twice the number of atomic orbitals available in the energy level that is being filled. For example, in the first period, only one atomic orbital is filled, hence the number of elements is 2. In the second and third periods, 4 atomic orbitals can be filled, therefore the number of elements is 8. In the fourth and fifth periods, 9 orbitals can be filled, hence the number of elements is 18. And in the sixth and seventh periods, 16 orbitals can be filled, and hence the number of elements is 32. The classification of elements across periods results in vertical columns of elements that have similar outer electronic configuration, same number of valence electrons, and therefore similar properties. In other words, they belong to the same family or group. For example, all the elements in group 1 of the periodic table have ns1 valence shell electronic configuration. Due to the presence of same number of valence electrons, all elements of this group are alkali metals that show similar properties. The only group that could have distorted this characteristic of all elements in a group having similar properties is group 3, that contains the lanthanoid and actinoid series of elements in periods 6 and 7. To avoid this discrepancy and to maintain the structure of the periodic table, these series are placed separately below the periodic table, thereby preserving the principle of classification. Thus, the long form of periodic table is in perfect accordance with the modern periodic law, keeping electronic configuration, which in turn depends on atomic number, as the basis of classifying elements. You have now reached the end of this module. In this module, you learned that the distribution of electrons into the shells and orbitals of an atom is called its electronic configuration. The electronic configuration of an atom defines its physical and chemical properties. The elements in the long form of periodic table are organized based on the principal quantum numbers of the last filled orbital. The periods in the periodic table indicate the value of principal quantum number n for the valence shell. The number of elements in a period is 2 times the number of atomic orbitals available in the energy level that is being filled. Therefore, the 7 periods contain 2, 8, 8, 18, 18, 32 and 32 elements, respectively. The elements in the same vertical column or group have similar valence shell electronic configurations, the same number of valence electrons, and therefore similar properties.